Good morning. Am I audible?
Yes, sir.
Okay, we'll wait just for a couple of minutes. Some more people, let them come in, and then we'll start. Okay, good morning again. Let us get started. Let others slowly join. Yesterday we talked about the basic concept of class and objects. And today and next week, we will develop fully on that to understand the power of object-oriented programming. Actually, we will slowly move more into object-oriented analysis and design, which is a very basic framework under which the design of a software can be made very compact with a good quality and good maintainability. So I hope my slides are visible, right?
Yes, sir.
So this is what we discussed at length yesterday. So I'll just give a quick reminder. The class is implementation of a type. So it's the only way to implement user-defined data type, which means a object of a class can behave exactly like any of the predefined built-in typed data. It contains data members, which are attributes, and has operations or functions or methods, member functions or methods. We'll see all of these through examples. It defines a namespace so that all data member or member function names within a class are unique to the class and will not get mixed with any global name or names used in other classes. And in this way, class offers a data abstraction or encapsulation, which is the first principle of object-oriented programming. And then we'll talk about access specifiers, which allow certain control on what data or which method can be used by other functions outside of the class, or which may not be usable by other functions of the class. And overall, the class defines a blueprint based on which several objects of a class can be instantiated. And for an object, the data members, the values of the data members at any point defines the state of the object, and member functions specify its behavior. Data members can be accessed, and member functions both can be accessed by the projection dot operator. And it has an identity, which is the address of the object stored in a constant pointer. This is just a summary of what we are going to see through the examples. Okay, so let's get started with the examples. So we will try to build types of some very simple entities that we come across regularly. C++ has support for integer, for floating point, float, double, but it has no complex data type. Complex numbers have two components, real component and imaginary component. So the question is, how do you model that? In C, you will simply model it as an aggregation because it has two components, RE and IM. So I say struct complex is this aggregation, and we are giving it a name, alias, which is complex, which, I mean, this name complex is nothing. Without the type def also I could have used it. Everywhere I need to write struct complex then. Instead of that, I can type def and just write complex. So I say complex. I have a variable declared here, which I initialize with a pair of values. Curly braces are used for denoting the pair. So this is something called an initialization builder list. We will talk more about that as we go along, but the values are just taken in the same order in which the data members are defined. So by this, RE gets initialized to 4.2 and IM gets initialized to 5.3. Then we can print them and see this. I can write the same thing now in C++. Instead of instead of struct, I use class. Class is a new keyword. I say class complex. Rest of the code apparently looks the same, and we will see where the differences will start coming up. So the main points are struct keyword in C is used for data aggregation, and class is a new keyword for data aggregation. So both are used for defining composition or aggregation builder. But class complex is a user-defined data type, and we will slowly understand what is the significance of user-defined data type is, where struct only aggregates, class aggregates, and will help to build an UDT. We have still not built that. We are just showing examples parallel to I'm sorry, parallel to C. So this is not yet the right way to write in C++, but this is what a complex uh, number objects that we can get. So in both these, complex is the class, which is a template or which is a blueprint, and N1 is an object that I have instantiated. In parallel, we will take look at this example, let's say. So I'm trying to define a point and a rectangle. So just assuming that it is on the integer grid. So possibly, say on your graphic screen, you see windows. So windows are always associated with rectangles. So they have a pair of points that they need to take, which is top left and bottom right, top left and bottom right. If you give these 2 points, then a rectangle is defined. So we are defining an aggregation, and we are using that aggregation, which is point, to define new data members here. Similarly, in parallel, in C++, we can have class point, class rect, and rest of the stuff you can do exactly similarly as you are doing here. You can see the initialization here. I'm creating an instance R of the of the type depth rect, that is this rectangle. So I need to give the initialization for 2 point data, each of which actually again is an aggregation of 2 values. So this aggregation 0, 2 will get initialized to TL, which is the top left, which in turn will initialize 0 to TL.x and 2 to TL.y. Similarly, 5, 7 will initialize BR. So BR.x will become 5 and BR.y will become 7. Same thing you can write in C++ using class. Yet another, this example on left you have done surely several times in your PDS course, creating a stack of, say, array, stack of characters, and you need a top marker to say where is the top of the stack. And initially, the top of the stack is put to -1 to indicate that the stack is empty. The same thing with class you can do. Okay, so these are the data members. So we have seen how to define the data members. Now we will get into, these are just reminders of the points that we are covering. Now we'll go into defining methods. This is something which you did not have in C. So again, I go back to the complex example. So I have a type def complex, and say I want to do 2 simple operations with this. One is finding the norm of the complex number, the normative value, which is the square of the real component plus the square of the imaginary component, square root of that. So I define a function double norm. Similarly, I write another function by which I can print a complex number. And then I can take this. I'm showing a call to print. It prints below the norm of this, because it is complex is calling norm and printing that norm value. So it says these are the 2 real and imaginary components, and if you take the norm, you get this. Now the difference. Here in C, when you take, both these functions are basically global functions, which mean that anyone can call these functions. That is one part. And there can only be one print function in the whole program. There can only be one norm function in the whole program, right? Which takes a value of the type complex. Here in class, we are doing a different thing. In class, we are writing these functions. Functions per se, as of now, have a similar body. Could have had same body also. I'm just changed the IO type, IO style in C++ to make things look more proper. But the main point is these have now become, this is the scope of the class. Starts at this curly brace after the class name and matches ends here, which is the end of class complex. Now the functions are defined within the class. Once you do that, that is what you call our member function. So they are like you have data members here, you have member functions here. They are called member functions, they are called methods, and so on. So when you want to invoke, C.print. C is your complex object type instantiated with initialization, and you will use the projection operator dot to invoke a method. So C dot will mean that C is of type complex. So the print function, which is defined within complex, will be used here. So this will call this function and eventually print the same result. You see certain difference in terms of the precision of the numbers printed. That is because of the difference between the format I have used in printf and the default format that exists in cout in the IO stream. Don't worry about that part. But the main thing is that functions can now become part of a class scope. So the first advantage that you can see that complex now is not only an aggregator, but it also has defined a namespace, because earlier in C, print was a global function. So I could not have defined another print function, because that will clash, that will say redefinition of the print function. But now print is in the scope of complex. So if I have another data type, say a fraction, where 2 I want to print, I can give the name to that function exactly as print and call it exactly in the same way. That these two names will not clash anymore, because the actual name of print here is complex : print, and in my fraction class it will be fraction : print. So that is the basic namespace meaning that we get from here. So we have data members and methods in this way. Rest of the examples are parallel in the same way. I have the rectangle, I'm computing area here, compute area, which is a global function. Here I'm writing the same thing within the class, so it becomes a member function. Same in terms of stack. This is the kind of stack that you must have written. I have the stack, I have an empty function, checking the top, pushing an element, popping the top of the stack, and then you initialize and initialize a constant string, push every character into the stack, and then over a loop you pop and take the top and keep on popping. So the basic effect is reversing the string. This example you must have done a number of times. Here the same thing I'm doing, but these functions now on left are now members of the stack class. So these are data members. Therefore, now when you instantiate S, you have to invoke the push of this push for this object behavior as s.push, which actually pushes. Similarly, you do s.top, s.pop for the other data members. So this gives you a very big advantage. For example, if you want to have some other data type, say DQ, double-ended queue, you wanted to use the same function as empty, you will not be able to do that in C because it is a global function. But in terms of C++, again, the namespace comes in. So DQ can have another method, its own method as empty. So everything is now owned by the class. Okay. So this is the basic encapsulation that we have achieved, that has operations methods and defines a namespace, and data is encapsulated in terms of that. Right? Now, given that, let us take a quick look into the identity. I talked about that identity of an object in C++ is the address of the memory location where that object is instantiated. It is a little bit, unnatural way to say address. So that's the reason I was making a parallel with the identification of buildings. Now, naturally, the identity of a building, the basic identity of a building is the geolocation of where it occurs, where it is positioned. So it's same kind of a concept. And every object can access that address by using this pointer. Now, this is again a keyword in C++. It's a fixed name, and it has a type which is like this. So if I have a class object, class X, then its this pointer looks like X star const this. You don't need to declare this. It's compiler implicitly knows, and that's always fixed. So what does it mean? We have seen the constness. So mentally we draw a vertical line at the star, and we see const is on the right side. So what it says that this is a constant pointer pointing to a non-constant data. Why this must be a constant pointer? Because obviously the object resides at a memory location, and it will be disastrous to be able to change that through the program. So that's only managed by the system. And this pointer is accessible only in methods. You cannot access this pointer in a function which is not a method of the class. So you can write use this pointer like this. You have a class X having two members M1, M2, and there's some other sample method where you are passing K1, K2. You can assign K1 to M1. Now, the compiler implicitly knows that M1 is a data member, so it will make that assignment to the data member. So you can do an implicit access, or you could explicitly refer to a data member saying that this pointer M2. What is this? This is the whole object, so the whole aggregate. So what is the, if this is a pointer to that whole object, then the object itself is start this, which is the dereferencing of this pointer, and dot is the projection of a component. So start this dot M2 is the M2 data member of this particular instance, any particular instance like we are talking about A here, that you will have. And you know, start this dot can be shortened in the notation, in the syntax, by this pointer M2. So this pointer M2 is the data member that you are talking of here. So this can be used. So you will question that why do I need to have this pointer? We will see several examples where without this pointer, it will be difficult to actually write the code. But in general, you may not want to use this pointer. You can just access like M1 here. So this pointer explicitly means implicitly passed to methods. So you can see here. So class X has a data member as a method F, which takes two ints. Now this is what we get to see. When it actually implements, when the compiler actually implements, it implements function F, whose name now is X::F because of the namespace effect. And it passes an implicit parameter, which is this pointer, which is X star const s, which is the address. So depending on which particular instance, for example, you have created an object instance A and you are calling a.f, but the actual call that it will make is X::F ampersand A, then the rest of the parameters. What is ampersand A? Ampersand A would be the address of A, which is the value of this pointer. And this is something that we don't have to do. We just don't bother about this. The compiler takes care of this. But by this mechanism, wherever you do this member function invocation, depending on wherever the object is, the function takes the parameters based on that particular object. So multiple object instances will get very easily distinguished at the actual translated binary level. So the use of this pointer, one that we have seen, it to distinguish between member and non-member, like you can use it for M2, but you cannot use it for M1, M2, you can use it. K1, K2, you cannot use it because they are not data members. But there are certain cases where you need to actually use it explicitly. For example, you are doing a doubly linked list and you are doing an append. So you pass a pointer. So you are appending a node after that, right? So you have the next set to this. Next is the forward link. So the node that you have passed will go at the end. So the current value of x is next is set to x, and x has to refer to the current object. So the previous pointer of x, the node that you are appending, must refer to the current object. So you need the address of the current object, and that is what you get through this pointer. So without this, writing such a code would have been very, very difficult. Similarly, suppose you want to define a increment function, say a pre-increment function for complex, which kind of would give you the same behavior as pre-incrementing an integer. So you want to do write a pre-increment method. So what it will do, it will increment, say, both real and imaginary components. That semantics is not important. You can define other semantics. But the point is the increment must happen on the same object on which this method is called, right? So the question is, how do you return its value? If you do use return by value, then what you will get is a copy of the incremented object, not this particular object having increment, because return by value makes a copy of it, we have seen. So it has to use return by reference, right? And what it will have to return? It will have to return the object on which it has been called, that same object. So what is that object? That object you will get through this pointer. So you return start this. This is a style you'll see very widely used to define a lot of fundamental functions and overloaded operators and so on. We'll see more examples of that. But you have to get comfortable using this. Its role of this in distinguishing a member, non-member is there, but that's not the significant use. Significant use is cases like this, where without this pointer, it would have been very, very difficult to write that code in an effective manner and create the data type. The final thing is every object, when it is created till it is destroyed, has a state, and that state is the object is an aggregation. So state is a collection of values that it has at any point of time. So suppose look at this example. I'm again doing a complex. 2 components, data members, and 4 methods. Get, which basically returns you the real component. Get im, which returns you the imaginary component. Set re, which takes a value re and sets it to the real component, and set im does it similarly. So if I now instantiate an object complex with 4.2, 5.3, then we'll say the state of C1 object is this pair of values, because it has 2 components. It's denotes a tuple or a sequence, as you say. Now, a method may change that state. For example, this is the initial state. If I do c dot set re 6.4, then what will happen? RE will get, this 6.4 will get assigned to the RE component. So 4.2 will now change to 6.4, and this is a new state of the object. But if you do get RE, you are just reading, you'll get 6.4, but that does not change the state. So a method may or may not change the state of the object. So the whole collection of values I'm sorry, that the data member has defines the state, and methods could change the state or they may not change the state. For example, in the last case here, you see im, you are doing a set im, so it is changing the state. Similar example, you can read through for better understanding more, if in reference to the point and class objects. So we have a rect created, and this is the initial state, and I have made here, instead of using a method, I've just made a direct assignment to the top left y component, y coordinate of the top left point. And naturally with that, this 5 changes to 9, the state changes. But when I do compute area, I'm just reading values to do compute area. There is no change of state. This is a longer example showing you in terms of the stack. So when you start and when you think of doing this, you can see here the way I have represented the state, because if you recall, stack has 2 data members, char data 5 and int top. So this itself is, it is an array, so this itself is an aggregation. So I've shown the aggregation of 5 elements, and top is another which gives the final aggregation of the whole class. I've put question marks because nothing has been initialized. In stack, you don't need to initialize. Then you initialize top, the state changes to top being -1. Then you push B. So what happens is B goes to the first element of the array, it becomes B, and top is incremented. You push A, top is further incremented. You check for empty, there is no change in the state. Right? You push again, it is top is incremented and T goes in. You check the top value, what is the top of the stack, there is no change of state. So you can see that out of empty, top, push and pop, empty and top does not change the state, push and pop changes the state. This is something which will come into the discussion several times later on. But this is the basic concept of a state of an object. So in object-oriented terms, what we have learned so far is we have learned to aggregate through classes. We have seen that that provides a namespace and it gets some kind of an encapsulation. We'll have to understand that encapsulation more. And now, because of the namespace, we can have multiple methods having the same name in different classes. We have talked about the identity of an instantiated object and its state as it goes through the different operations in the program. So let me stop once and see if you have questions before I go forward. Any questions, friends? No question. This was easy, I think.
Yes, sir.
Yes, please.
Sir, by initializing the values in the class, is the manner similar to as when we do by structs, like from left to right?
Yes, exactly. But there will be lot more into it as we go through, partly today and then next Wednesday, of details of how you initialize. Initializing an object is a very, very critical aspect of C++ object creation. And you will see how it gives you a very, compact, error-free mechanism, which is very error-prone in terms of C programming using struct. So, but we'll come to those details. But anything, I mean, C++, just take it this way, that C++ is completely backward compatible to C. And class is designed in a way so that it is backward compatible to struct. So whatever you can do in struct, you can also do in class, though not the other way around. Okay.
Yes, sir.
Any other questions? Let me proceed. But just feel free to even stop me in the middle and ask questions. Okay, now we'll get into the core of the encapsulation concept, which is access specification. The point is, we have been loosely talking about the fact that certain data members or methods can be used from outside, certain cannot be used from outside. So that leads to that originates from a core concept of object orientation, which is information hiding. I have made the class to create an object which has its own identity and state, and I would like not to expose every part of that information to the external world. I will do that on a need basis. And what is the mechanism of doing that, and what advantages does it give us? Okay. Now I have on left, I have a class. I'm using this keyword public. Public means everybody can access. So I'm saying public and then rest of the data members. So I'm saying both data members are public. My norm function is public as well. And just to illustrate, I have here written print not as a member function, but outside of the class as a global function. So it is public data, public method. Look at right. I'm writing exactly the same aggregation, but I've changed the keyword at the data member part. I'm calling it private. Rest of it is the same. This is just this one word is the difference. Now, in the left, when I write the code to print, I'm given a complex object T, and to print, I will need to access the RE component and IM component. So I write T.RE, T.IM, and it prints pretty well. It initializes and then prints. Okay. Now, when I try to print here with this keyword changed to private, which is a print is a global function again, then the compiler gives me an error complex : RE, this component cannot access private member declared in class complex. Just see the difference. Norm uses the component RE. There is no error given on norm. Why? Because norm is a member function of the class. It is within the encapsulation. By private, I have hidden the data that the class has. I have exposed the method norm by public. So when a function from outside of the class, that is, which is not a member function, a global function, or similar examples will apply to member functions of other classes also. When it tries to access T.RE, the compiler finds that complex class has defined that to be non-accessible from outside, defined it as a private. So it will give this error and this code will not compile. Similarly, same error will be thrown on T.IM. Now, coming to the main function, I have jolly well initialized it here. Here, I have not changed anything, but here I'll get an error. Why would I get an error? I'll get an error because to be able to initialize C with this pair 4.2, 5.3, I'm implicitly in a different notation making an assignment of 4.2 to C.RE, 5.3 to C.IM. Main is a function which is obviously not a member of complex. So it is external to the class. These data members are private. It has no access rights on them. Therefore, even this initialization will be given an error on, but it will not be so apparent because the compiler treats it little differently. It treats this as an initializer list. So it will say that I cannot convert this initializer list onto the complex object, right? So these red ones are the differences. So this is a very, very strong tool at the hand of the developer, and this is where the designer, the developer always has to make a judgment as to which part of the class should I expose to the external world and which part should I hide from the external world. So to come to the access specifiers, these are called access specifiers. The access specifier could be for members to enforce data hiding, and will separate the implementation and from interface. Again, another two very key concept of object orientation. We will slowly unfold through examples. So private is an access specifier which is accessible inside the definition of the class, as we have seen. So only the member functions of the same class can access the data which are private in that class. Public is something which is accessible everywhere. They can be accessed by member functions of the same class. They can be accessed by member function of a different class. They can be accessed by global function. The keywords public and private are the access specifier. And there is a default that if you do not specify something, then the compiler goes conservative and assumes that you are saying private. Right. So because there is more risk to expose than expose something which you should not have done than to hide something which you should have actually exposed. And a class may have multiple access specifier. So you can write private, then a set of members, then public, a set of members, then again private, a set of members. The access specification continues till you come across the next access specifier. Right? So what is the kind of design protocol that we should use? What we are saying is there are details in terms of the object, how it is implemented, and that details is what we say is the implementation of the object. Right? For example, I'm interested in the notion of complex. Now, the fact that I'm using a pair of double to represent that is my choice. I could have, instead of a pair of doubles, I could have used an array of size 2 of double. For whatever reason. I'm doing a stack. You have studied stack in PDS, and you know that stack can be implemented as an array. It can be implemented as a linked list. Now, how I implement that is my choice. How I keep that data, how I do the navigation on that data structure is my choice, which I do not want to tell the external world. But at the same time, for my data structure to be useful, for my user-defined type to be useful, there must be certain ways of using that. So the ways of using a complex data type is to be able to find its norm, to be able to print it, etc., etc. To stack, you know very well. Its use is in terms of empty, top, push, and pop methods. As long as users of the stack can access these methods, they should be happy and just continue with their programming without bothering about internally how the implementation is done, whether it is an array or it's a linked list or it's something else. Right? So that is the difference that we are making, that we identify which I think is the private part of my class, my object, specific to implementation, and which is for use to everybody. Right? Now, customarily, I'm saying customarily, and that is the kind of rule 1 of object design, is you put all attributes, data members, in private part and put all methods in the public part. So you have the data should always be hidden. That is, the pair double RE should be private. The stack array and the top pointer should be private, because you want to hide those details, you want to protect those details. And the methods should be in the public part, because they are the interface by which objects can be actually used. So state of an object can be changed only through one of its methods. So if the data is, all data is private, then there is no way that you can change that data, because changing any of the data changes the state of the object, right? You cannot change that state without the object getting to know it, because you have no access rights for doing that. Whereas the behavior of an object, which is coming through the interface, is accessible through the methods which anybody can do, because that is the purpose for which you are building the class, you are designing the class, and you are instantiating objects. So this whole principle of separating out implementation from interface, or interface from implementation, is a principle of information hiding, and that is the key concept of, or the basic concept of object oriented design. Now, for the sake of efficiency in design, we at times will also put attributes in public, or we will put methods in private. So the public attributes kind of should not decide the state of an object. I mean, by theory they will, but it is not the state that you are really bothered about. Right? You may allow a public attribute to let your user keep some data as a part of the object, which is not going to affect the behavior of that object. Similarly, private methods are not part of the behavior because nobody can use them, but often it is, maybe if you have complex behavioral methods in the public, to implement them, you may need to have a better structuring in the procedural sense, and need to have some methods which you do not want the public to know or to use. So under those circumstances, you can make methods private, but the default design principle is data should always be private, methods should always be public. Okay? So let's look at examples. So back to the stack. So stack class, as we had written before, and this is the what is it? Oh, it's doing the reverse string again. So here everything is public. So I not only can use empty push pop top, but anybody can directly go to s.top and change it. Go to any data element and change it. Now I write it on this side. Is the same methods. It's everything is in public still, and I'm just showing you initially a different choice that you can make is, so I'm just showing that it could be, as I said, that it could be implemented in a different way. You know about stack implementation in terms of array and in terms of linked list. I'm showing you another third option, which is available in C++, particularly in C++ template library. There's something called a vector. So we will come to details of for what vector is or what does this mean. The bottom line is this says that it is a vector of character. Vector pretty much is like an array, but with the, I mean, it can be used in the same way you use array. As you can see here, I have defined data as vector and then using the array operators to access it. But the basic advantage of the vector is it does not have necessarily need to have a fixed size. Arrays are fixed by size, and that becomes a difficult bottleneck for stack. And that's the reason you move from going from array implementation of stack to linked list implementation of stack, because array implementation of stack gives you a limit in terms of how many elements could be there in the stack at a given point of time. Whereas linked list implementation makes it flexible, but it makes the stack operation much slower. It takes a lot more of memory. So vector is a very good trade-off. And when you write in C++, in a large number of cases, you should consider whether you should define an array or you should use a vector. And because vector can be resized. So that's precisely what I'm doing here. So I get s dot data here is creating an dynamically creating an array of 100 elements. In vector, initially it will have some size. I do not know how many elements it will allow. I do not know. But all that I'm saying is I can resize it to 100. This is a vector is a class. Vector character is a class, and data is a member of that. Data is an instance of that. So for the stack object, I come to this data member, data underscore, and invoke the method resize, which will make the vector size 100. And then I will do s.top as -1. So both are exposed initializations that exist, right? So students, just excuse me for a minute. There's a door call. I'll just be back in a minute. Sorry about that. I'm back. Okay. So but everything is public here, the data as well as the methods. So I can set it from outside. But here I just have tried to show you that there could be alternate implementations of the stack. Now I have gone to the next example. Everything is same on the top side. Up to this point, everything is same. And then let's say it may be inadvertent, of course. 2 is assigned to this stack, top of the stack. I have inserted 5 elements. And then if I change, so the value of top at this point should be 4. Right? That is that's the topmost element, because 5 elements have been inserted 0, 1, 2, 3, 4. But I can make a direct assignment to top, and once I do that, my whole stack, the whole concept of the stack is completely devastated. The stack gets inconsistent. I can do that here as well. That is the key issue of separating interface from the implementation. This is my implementation. Char star data in top or vector char data in top. These are my implementation. These are my interfaces, what people use. So using only those interfaces, as you have seen, using the push here, using the empty, top, pop, all 4 functions are used. With that, the user can get all the requirement. But by keeping my implementation exposed, I have created the possibility of inadvertent error. And that pulls down the quality of my program, of my design. So how should I do it? Very simple. The implementation part, which is the data organization, I've made them private here. And then I write the whole thing. Once I have made them private, 2 things happen. One is I cannot write any of these. I cannot write the s.data top. Of course, the question of error is not there. So when I when I do this, then I need a way to initialize the object, initialize the state to something consistent. For example, for a stack, that initialization of a consistent state means that top is -1. For if you are doing with this, initialization mean that this is a cat star pointer, so there must be enough space acquired to keep my stack. So these two things going back, these two things here, or this resize here is what was required. So when you encapsulate, that initialization has to be encapsulated as well. And that is a special way of doing that, which we say is constructor destructor. We will talk in detail about that in the next module. But this is what it does very simply. It is a method which you define having the same name as the class, and then in a list you give this initialization. So this says new on char for 100, put it to data, put -1 to top. Similarly, you are doing top to -1, and then in the function body we will see what is the difference of writing it in this list and what is the purpose of writing it inside the body. But the bottom line is this does the initialization. And the beauty of the whole separation is now when I make the object stack, it automatically invokes this function. I do not have to do anything. All that I have to do is to make it available in the interface part. So I do not have to call this function. This gets automatically called at this point. This gets automatically called here. So my stack will be ready as soon as my object is instantiated. Similarly, when if I go back to this previous example, I had dynamically allocated some data to keep the stack. So I had to use a delete, array delete to clear those. If I forgot, then memory will be leaked that I will have no way to regain that back. Here, I have a deinitialization method, which is called destructor. It's written with tilde followed by the stack name, where I have put this cleanup. Now, the beauty again is as the initializing constructor gets called at this point, when the object goes out of scope here, it is in the scope of main. When it goes out of scope here, the compiler automatically calls the corresponding destructor. So you don't have to remember that you have to create an, if you have to acquire the memory or you have to release that memory. That will happen automatically. And things like, going back one slide, things like s.top getting assigned to 2 by inadvertent use is no more possible, because if you try to write that, since top is a private data member, you will get a compilation error at this point. So this is the basic hiding principle that and its implementation in C++ that you do. So you could write these interfaces inside the class, or you could just say that this is my, please mute yourself. This is my implementation and this is my interface. Please mute. And then separately define every function outside of here. Obviously, when you try to define externally, every function name has to be prefixed by the class name because it's a namespace. So one is called the in situ. You can write inside the class definition, or you can write outside. There is an advantage of writing it outside because this is all that your user needs to know. So it can go to a header file which the user includes and can pretty well, jolly well, use your stack. Whereas these implementations details goes into a different source file where those details are not important, right? So I think we are, and then you can, if you want some of those implementation details to be exposed, you can obviously write get or set functions as we did in the earlier example. So that's the access specifier, which gives you the core idea of implementation, information hiding and isolation of implementation from the interface, which is the very core thing. So I'll stop here. Before we quit, if there is a quick question I can take, we are already on time. Ayan Singh, can we return this pointer to main function and access its private members from main function? No, you won't be able to, because if you could, then you are breaking the encapsulation. So that's a compilation error. So first of all, Aman, there is no rationale in terms of writing a code where you provide a function in the interface which returns the this pointer to you, because then you are actually exposing your implementation. So that's your choice. But even if you do that, then it will I mean, through backdoor you could be able to do. You can cast it to something else and then use that so that the type checking is broken. So it is like a tool. We are being given a toolbox, a set of knife. What we use it for, whether we cut vegetables or we cut our finger, is our choice. We have to be careful not to cut our fingers, but cut vegetables in the right way. We'll talk more about that. We are completely out of time now. So see you in the next class. Just a quick announcement. The laboratory teachers will also tell you that there was a assignment on C++ which was given this Wednesday. So we have decided to extend the submission deadline for that assignment because that assignment needs far more understanding of C++, which we are doing in this class. So it will only make sense for you to do that assignment after we have learned these things well in the class. So I had a discussion with Professor Shorangshu and Abir. They will postpone the assignment submission date for it, and a new assignment will be given in the next Wednesday's class. So, but this will come as an official announcement from the your laboratory teachers. I'm not your laboratory teacher, you know. Okay, thank you very much. So let me have a nice day. Let me just close this class now and see you next week.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.